So, okay. So, good day. So, we will have our fourth example for stresses in beams, specifically bending stresses. Okay. So, we will choose 5.8. Okay. So, for the beam shown, calculate A, the maximum bending stress, and B, the bending stress of a point 0.5 inches from the top of the beam on section D. Okay, so this will be our beam and its cross section area. Okay, without further ado, we will explain its solution. Okay, so this will be our solution. Okay, so I just copied uh, the problem and then uh, the diagram. So here I already put the reactions. Okay, so in this portion it is pinned, so it has AY and AX, and in this support at E, it is roller, so it has only one reaction, which is vertical. Okay, and its cross section area is 2 inch and 4 inch. Okay, so I have already solved it in advance. Okay, so I have already I computed the values of the reaction by summing up forces horizontal and vertical equal to 0, and sum up moments is equal to 0. Okay, so I used the three equilibrium equations in order to determine the reactions. Okay, so from here we have sum up forces at x is equal to 0 to the right as positive. So here, okay, so assuming that these uh, values are not solved yet. Okay, so AX, there is no other horizontal forces you can see in this beam, so therefore AX is equivalent to 0, and then we have sum up forces of Y is equal to 0. Okay, so from this beam, okay, so we have AY then plus AY is equal minus 2,000 is equal to 0. Okay, so that is your equation. By using sum up forces, vertical equals 0. Okay, so since we did not have computed yet AY and AY and EY respectively, so we need to find uh, the value of any of this. Okay, so we sum up moments at 0 at point A. So at point A, so relative to this point, this 2,000 libra will rotate clockwise. Okay, it will rotate clockwise here. So here, see, we assume that counterclockwise is positive, so therefore negative 2,000 times the moment arm, which is 3, then plus 12 times, okay, so I'm sorry, it should be EY. So it should be EY here. Okay. Plus EY times 12. So we got EY is equal to 500 libra. Okay. So I have already put it here. And then since we know the value of EY, so therefore we substitute from this formula. So we get 1,500 libra. And since we got both positive values, so therefore our initial assumption that AY and BY are upward respectively are correct. Okay, so since we know that AY is 1,500 libra and EY is 500 libra, so we can draw its moment diagram. Okay, shear and moment diagram. So this is the shear diagram and this is the moment diagram. Okay, so here, since we have an upward force of 1,500, so our first shear at x is equal to 0 is 1,000 equal to 1,500, since there is no other force at the top. So 1,500 libra. Okay, from this to this. Okay, so secondly, we have 2,000 libra. So from this point, which is 1,500 libra, it will suddenly drop linearly. Okay, vertically linear by 2,000 libra. So 1,500 libra minus 2,000 libra is negative 500 libra or pounds. And then since there is no force existing here, so your negative 500 libra will continue till the end, till the left side of the end, negative 500 libra. And then at the right side, since we have 500 libra upward, so from negative 500 libra left, it will become 0 at the end. Okay, so we have that. So since, okay, so it is known that the area under the shear diagram is equivalent to the value of your moment. So therefore, okay, to compute this area, so we have 1,500 times the length, which is 3, because this is a square, so we have 4,500 libra foot. And since this is a straight line, 0 degrees, so this will be a 1 degree or a line with a slope. Okay, and then since this is a negative area here, this 4,500 libra foot moment will then again diminish from this point, since at this point from x is equal to 3 to x is equal to 12 has a negative area, so it will linearly go downwards since this is constant negative 500 from x is equal to 3 to 12. Okay, so it will become it will diminish linearly. Okay, so that is your shear and moment diagram. So from that, we now know what is the value of your maximum, your M max also. So this will be our M max. Okay, so we know our M max is 4,500 libra foot. Okay, so we use it. Okay, so we find the maximum bending stress. So we can compute down the maximum bending stress. So we have M max over S. Okay, so first we multiply 4,500 libra foot by 12 inch over 1 foot. Okay, so in order to convert it into libra inch, and then divided by the S. So we all know that the S of a rectangle is BH squared over 6. Okay, so BH squared over 6. So your B is 2 inch and your H is 4 inch respectively. Okay, so we have 2 inch times 4 inch squared over 6. So if we simplify this one, we will get the maximum bending moment as 10,125 psi, if it, or 10.125 ksi. Okay, so here we now try to find the bending stress at 0.5 inch from the top of the beam on section D. Okay, so we find, okay, 5 inch from the top of section D. So first, we must compute the moment at D. Okay, so here, so the moment at D is equivalent to 4,500 minus, okay, this area from 3 to 6 meter. Okay, from area, so we have negative 4,500 minus 500 times the length, which is 6 minus 3, which is 3. Okay, so 4,500 minus 500 times 3. So we will have 3,000 libra foot. So from that, then, so we can compute, okay, so considering this stress diagram of this cross-sectional area, so this is your bending moment at the top, at D, okay, at the top of D. So from here, it is located 2 inches outside of the neutral axis. So this is the neutral axis actually here on this line. Okay, so 2 inch. So we need to find the stress at this point. Okay, at that point. So first, we need to compute the bending stress at D. So specifically at the top of the D. Okay, so we got 3,000 libra foot. Okay, so you convert it into libra inch by multiplying 12 inch over 1 foot divided by the section modulus, which is BH squared over 6, or 2 inch times 4 inch squared over 6. So we got 6.75 KSI. So that's not the answer yet. Okay, so we gonna have a ratio and proportion, okay, using this triangle. Okay, so since from 6.75, okay, 6.75 KSI, it will linearly diminish up to 0 at the neutral axis, but somehow it is located, okay, 0.5 inch at the bottom of D, from the top of D. So it is located 1.5 inch from the neutral axis, where your stress is theoretically 0. So we will have a ratio and proportion by similar triangles. Okay, so um, bending stress at D over 2 is equal to bending stress 0.5 inch from the top of D. Okay, so from that, we all know this is 6.75. So therefore, this, or the bending stress 0.5 inch from top of D, is equivalent to 6.75, since this is 6.75. Okay, this is actually 6.75 in value. So we will multiply it by 1.5. Okay, this 1.5, and then divided by 2. So we got 5 point, okay, the stress, the bending stress at 0.5 inch from the top of D, we got it as 5.0625 KSI. So here are the answers for A, for maximum bending stress and bending stress 0.5 inch from the top of D. So these are the answers. Okay.